High in the Atacama Desert of Chile, the air is thin, cold, and almost perfectly free of moisture. It is one of the driest places on planet Earth, a hostile landscape of rust-colored rock and dust that more closely resembles the surface of Mars than it does our own world. And it is for this very reason that humanity has built its greatest eyes here to stare into the silent black expanse of the cosmos. One of these eyes is not like the others. It isn't searching for beautiful nebulae or distant galaxies. Its mission is far more urgent. It is called the Asteroid Terrestrial Impact Last Alert System, or ATLS for short. 365 days a year, it scans the heavens for one thing: killers. Its software is programmed to detect the faint glint of approaching asteroids, to calculate their trajectories, and to sound the alarm if one is on a collision course with our home. It is Earth's silent guardian. But on July 1st, 2025, it detected something new. The system flagged an object, faint and unassuming. But as the data poured in, a chilling realization began to dawn on the astronomers watching. This object wasn't a threat in the way ATLS was designed to expect. It wasn't on a collision course. In fact, its path was far stranger. It was moving too fast. Impossibly fast. It was an intruder, a trespasser that had breached the borders of our solar system from the outside. The silent alarm had been triggered not for an attack, but for an arrival. To understand the profound shock of this discovery, you have to understand the fundamental rule of our solar system. Every object born here, from the colossal planet Jupiter to the smallest pebble in the asteroid belt, is bound by the sun's immense gravity. Think of it as an invisible leash. Every planet, every comet, every asteroid is on a leash, forcing it into a closed path called an ellipse. They go around and around and around. They are prisoners of the sun, destined to repeat their orbits for billions of years. We can measure the shape of this leash with a number, a value known as orbital eccentricity. An eccentricity of 0 is a perfect circle. An eccentricity between 0 and 1 is an ellipse, the standard leashed orbit of everything we call our own. For centuries, every object we had ever charted in our cosmic neighborhood followed this rule. But this new object, the one found on July 1st, broke the rule. Its trajectory was the astronomical equivalent of a smoking gun. When scientists calculated its orbital eccentricity, the number that came back was not between 0 and 1. The number was 1.8. This value describes a completely different kind of path. It is not a closed loop, it is not a leash. It is a path known as a hyperbola. A hyperbolic trajectory is a one-way ticket through the solar system. It is the path of an object that has come from the vast, empty darkness of interstellar space, fallen towards our sun, and will then be violently flung back out into the void, never to return. Imagine a bullet fired from a rifle trillions of miles away. It screams past our sun, using its gravity like a slingshot to gain even more speed, before continuing its journey into the infinite black. That is the crime scene. That is the impossible trajectory. This single number, 1.8, was irrefutable proof. This object was not from here. It was not one of ours. It was a visitor, a relic from another star system, and for the first time we had caught it right as it was walking through the front door. The investigation had just begun. Before an object can be investigated, it must be given a name. In astronomy, this is a rigid and formal process, a chain of custody for evidence. Immediately after its detection in early May of 2025, the intruder was assigned a provisional designation by the global authority known as the Minor Planet Center. Its first official name was C/2025 J1. This isn't just a random string of characters. It is a code, and it tells a story. The C signifies that the object is a comet, and specifically a non-periodic one. This means its orbit is either longer than 200 years, or, in this case, not an orbit at all. The 2025 is straightforward. It is the year of discovery. The letter J tells us precisely when it was found. The year is divided into 24 sections, and J, finally, the number 1 means it was the very first comet discovered during that specific 2-week window. But this name was only temporary. As observatories around the world confirmed its impossible speed and its origin from beyond our sun's grasp, it was given a new, permanent and far more profound designation, 3I/Atlas. The I stands for interstellar. The 3 means this is only the third such object ever to be confirmed in all of human history. And Atlas honors the robotic telescope system that first sounded the alarm. This name change was the official verdict. It was the moment the scientific community declared, with one voice, that this was no longer just a comet, it was a certified alien, a traveler between the stars. To understand the investigation into our third interstellar visitor, we must first exhume the files on the 2 that came before it. These are the cold cases, the precedents that define the entire manhunt. The first case file was opened in 2017. It was the first time humanity had ever confirmed with absolute certainty that we were not alone in a cosmic sense. An object had entered our solar system from the outside. It was designated 1I/ʻOumuamua, a Hawaiian name meaning the first distant messenger, or, more poetically, a scout sent from the distant past. And it was a scout unlike anything we had ever imagined. We never got a clear look at it. ʻOumuamua was just a single point of light, too small and too far away to resolve with any telescope on Earth. But we could watch how that point of light behaved. As it tumbled through space, its brightness changed dramatically by a factor of 10. This told scientists that the object had a truly bizarre shape. To produce such a wild swing in brightness, it had to be extremely elongated, perhaps 10 times longer than it was wide. The initial theories painted a picture of a cosmic cigar, or perhaps a perfectly flat pancake-like shard, tumbling end over end through the void. But its shape was not the strangest thing about it. As ʻOumuamua passed the sun and began its long journey back out into the darkness, astronomers noticed something that defied the laws of physics as we knew them. It was accelerating. It was pushing itself away from the sun with a small but persistent force that could not be explained by gravity alone. For a normal comet, this is expected. As a comet warms up, ice on its surface turns to gas, creating a jet-like effect that gives it a gentle push. This is what creates a comet's beautiful, visible tail. But ʻOumuamua had no tail. It had no visible outgassing. It was a ghost, pushing itself along with an invisible engine. This single, irrefutable fact ignited a firestorm of scientific debate. How could it be moving itself without any visible means of propulsion? Some scientists proposed it was made of something exotic, like a pure nitrogen or hydrogen iceberg, whose outgassing would be completely invisible to our telescopes. Others, most famously the Harvard astronomer Avi Loeb, put forward a more radical and unsettling hypothesis, that the object's strange acceleration and shape were consistent with it being an artifact. A piece of technology, a solar sail perhaps, designed to catch the light of stars, sent from another civilization. ʻOumuamua left our solar system, leaving behind only questions, establishing the precedent of the interstellar visitor as a profound and unsettling anomaly. Just 2 years after the baffling passage of ʻOumuamua, the second stranger arrived. And if the first visitor was a mysterious anomaly, the second was a comforting dose of normality. It was discovered in 2019, not by a giant state-of-the-art survey, but by an amateur astronomer in Crimea named Gennady Borisov. Using a telescope he had built himself, immediately 2I/Borisov, named in his honor, looked different. Where ʻOumuamua was a clean, star-like point of light, Borisov was fuzzy and indistinct. It had a visible coma, the classic hazy atmosphere that surrounds the nucleus of a comet. And trailing behind it was a faint but unmistakable tail of dust and gas. In short, it looked exactly like a comet. As it got closer, the world's most powerful observatories turned to stare. The evidence that poured in was overwhelmingly, almost boringly familiar. When Borisov accelerated away from the sun, its push was perfectly explained by the amount of gas and dust seen pouring from its surface. There was no mystery engine here. The cause and effect were clear. When astronomers used spectroscopy to analyze the light coming from its tail, they found a chemical fingerprint that could have come from our own backyard. They found cyanide. They found diatomic carbon. These are the very same building blocks we see in the comets that were born and raised right here in our own solar system. It was the ultimate control group, Borisov proved that comets from other star systems could be, and perhaps usually are, just like our own. It was a piece of another solar system, yes, but it was a piece that followed all the rules. By being so perfectly normal, Borisov served to make the memory of ʻOumuamua even stranger. The second visitor showed us what to expect. Its predictable behavior only deepened the mystery of the first. It established the other, opposite precedent, that of the interstellar visitor, as a familiar cousin, a simple traveler passing through. So this is the legacy our newcomer, 3I/Atlas, inherits. It arrives on a cosmic stage set by two profoundly different predecessors. These two case files represent the two extremes of what an interstellar object can be. On one hand, we have the anomaly, 1I/ʻOumuamua, a bizarre, fast-tumbling, oddly shaped enigma that accelerated without a tail and defied any easy explanation, leaving a trail of controversy and speculation in its wake. On the other hand, we have the control group, 2I/Borisov, a perfectly normal, well-behaved comet that just happened to have been born trillions of miles away. It was a reassuring sign that the chemistry that formed our solar system is not unique in the galaxy. This brings us to the crucial question that defines the entire investigation. Into which of these two categories does our third visitor fall? Is it another ghost, a silent tumbler that will deepen the mystery and force us to once again question our fundamental understanding of the universe? Or is it another piece of the puzzle, a familiar face that helps us build a clearer picture of how star systems are formed across the galaxy? There is only one way to find out. We have to follow the evidence. We have to put this new suspect under the most powerful microscope humanity possesses. The remote autopsy was about to begin. The suspect, 3I/Atlas, is millions of miles away. It is a ghost in the dark, a single, unresolved point of light even in our most powerful telescopes. We cannot send a probe to sample it. We cannot get a close-up look. So how do we perform an autopsy on a ghost? How do we read its secrets from across the vastness of space? The answer lies in the one thing the comet sends directly to us. It's light. Light is the ultimate messenger, and the science of decoding its message is called spectroscopy. It is one of the most powerful tools in all of science, and it is the absolute foundation of our remote forensic investigation. To understand how it works, think of the light from our sun. We see it as white or yellow, but it is actually a perfect blend of every color in the rainbow, all mixed together. When that full-spectrum sunlight travels through space and hits the cloud of gas surrounding the comet's nucleus, its coma, something amazing happens. Every element, every molecule in the universe has a unique secret identity. When light shines through a cloud of a specific gas, like hydrogen or water vapor, that gas gets excited and absorbs very specific colors or frequencies of that light. It plucks them out of the rainbow. It doesn't absorb the colors next to them, only its own signature frequencies, leaving behind dark, empty gaps in the spectrum. These gaps are a fingerprint. They are a barcode. If you see a pattern of gaps that matches the known barcode for water, you know with 100% certainty that water is present. If you see the barcode for sodium, you know sodium is there. Every substance has its own unique, unchangeable barcode written in the language of light. So the process is this. Our telescopes on Earth act as giant buckets, collecting the faint, ancient light that has traveled from the sun, passed through the comet's gassy coma, and then journeyed all the way to us. That light is then channeled into an instrument called a spectrograph. The spectrograph acts like a hyper-precise prism, taking the blended light from the comet and splitting it wide open into its full rainbow of colors. When we look at this stretched-out spectrum, we don't see a smooth, unbroken rainbow. We see a rainbow with dark lines running through it. These are the absorption lines. These are the gaps. They are the fingerprints left behind by the chemicals in the comet's atmosphere. Our job, as forensic astronomers, is to match those fingerprints to the known culprits in our chemical database. It is how we can tell you what a star is made of from 1 billion light-years away, and it is how we were about to read the very soul of our interstellar visitor. The ghost was about to talk. With the principles of spectroscopy established, the trap was set. As the light from 3I/Atlas poured into spectrographs around the world, scientists began to analyze the barcodes hidden within it. They were hunting for clues, for anything that would place the suspect at the scene of a familiar crime. And very quickly, the results began to materialize. The first and most important fingerprint they found was water. The characteristic absorption lines of water molecules were clearly present, etched into the light. This was a monumental discovery. Water is the solvent for life as we know it, but in cometary science it's also a sign of familiarity. The vast majority of comets born in our own solar system are at their core dirty snowballs, rich with water ice that turns to vapor as they approach the sun. Finding water in our interstellar guest was the first major piece of evidence suggesting it might not be so alien after all. It was a point for the Borisov column, a vote for normality. The second fingerprint they identified was cyanide. Now, the word cyanide understandably sets off alarm bells, but in the context of the cosmos, it is not a poison, it is a promise. Cyanide, a simple molecule made of one carbon and one nitrogen atom, is one of the most common and important building blocks found in comets. It is a key ingredient in the formation of amino acids, the foundation of proteins. Finding it here was another check mark in the normal column. It told us that the same prebiotic chemistry that may have seeded life on Earth is also happening in planetary systems around other stars. The third major finding was diatomic carbon. This is a molecule made of two carbon atoms bonded together, and it is almost a trademark of comets. When it is energized by sunlight, diatomic carbon glows with a distinct ethereal green light. This is what gives many comets their beautiful green coma. Its presence in the spectrum of 3I/Atlas was yet another powerful link, tying it not to the bizarre, inert nature of ʻOumuamua, but to the classic, active behavior of a traditional comet. The evidence was piling up. Water, cyanide, and carbon. The chemical profile was clean. The fingerprints all matched those of a local suspect. The initial verdict was in. 3I/Atlas was looking less like a mysterious anomaly and more like a simple traveler, a cousin from a distant but chemically similar star system. It was, for all intents and purposes, a second Borisov. But in any good investigation, when the evidence seems too clean, too perfect, that's when you have to look closer. And there was one piece of evidence that just didn't fit. The initial forensic report on 3I/Atlas seemed straightforward, almost disappointingly so. The chemical fingerprints were all there: water, cyanide, diatomic carbon. The evidence pointed towards a standard garden variety comet, a near twin of the second visitor, Borisov. The case appeared to be closing, with the verdict leaning towards familiar traveler, but a single piece of physical evidence refused to fit the narrative. It was the tail. In the courtroom of celestial mechanics, a comet's tail is a key witness. It tells you about the forces acting upon the suspect. There are two main types. The gas tail, or ion tail, is made of vaporized material blown straight back by the solar wind. It points directly away from the sun, like a windsock in a gale. The dust tail is different. It's made of heavier, solid particles that are pushed more gently by the pressure of sunlight itself. These particles get left behind in the comet's orbit, creating a broader, more curved feature. The problem with 3I/Atlas was the relationship between its gas and its dust. The spectroscopy results, while clear, showed only a modest amount of gas being produced, particularly water vapor, which is the primary engine for cometary activity. A modest engine should produce a modest tail, but that is not what telescopes were seeing. They saw a large, impressive dust tail. It was far more substantial and significant than the measured gas output could account for. The witness was contradicting itself. It was like seeing the smoke of a raging bonfire but looking closer and finding only a single smoldering log. The effect was all out of proportion to the cause. This was a profound contradiction. How could the comet be shedding so much dust with such a weak gas engine? This single question reopened the entire case. It threw the simple, clean verdict into doubt. Scientists were forced to consider more complex scenarios. Perhaps the dust particles were extraordinarily fluffy, like cosmic snowflakes, so light that even a gentle breeze of gas could launch them into space in huge quantities. Or maybe the comet was releasing a different kind of gas, one much harder to detect, like carbon monoxide. which could be driving the activity invisibly. A third theory was even more compelling, that the comet had recently undergone a violent outburst. A pocket of super-volatile ice deep inside may have suddenly flash-heated, exploding outwards, and releasing a massive cloud of dust all at once. If that were the case, we were now just seeing the aftermath. The gas from the explosion would have dissipated quickly, but the heavier dust cloud would linger for weeks, a slowly expanding crime scene. Whatever the cause, the strange dust tail proved one thing: this visitor was not a simple Borisov clone. It had its own secrets, its own unique story. The initial simple autopsy was over. Now, a deeper, more complicated investigation had to begin. The mystery of the oversized dust tail led investigators to a chilling new hypothesis. The evidence wasn't contradictory if you changed your fundamental assumption about the suspect. What if the comet wasn't a solid object being pushed by gas jets? What if the comet was simply falling apart? This theory paints a picture of an incredibly fragile suspect. Comets are not solid monolithic rocks. They are known as rubble piles, or more accurately, icy dirt balls. They are loose collections of ice, dust, and rock, held together by their own feeble gravity and frozen gases acting as a weak cement. They are among the most delicate and structurally unsound objects in the entire solar system. As our interstellar visitor plunged towards the Sun, it was being subjected to immense and relentless torture. First, there is the thermal stress. The side facing the Sun could be heating to hundreds of degrees, while the side facing away remains in a deep freeze, colder than liquid nitrogen. This incredible temperature difference creates enormous internal pressures, cracking and splitting the nucleus from the inside out. Second, there are the tidal forces. Just as the Moon's gravity creates tides in Earth's oceans, the Sun's colossal gravity was trying to stretch the comet apart. The pull on the side of the comet nearer the Sun was significantly stronger than the pull on the far side, a constant tearing force. Finally, as what little gas it had did escape, it would fire off in uneven jets, causing the nucleus to spin. If it spun fast enough, the centrifugal force alone could be enough to overcome its weak gravity, flinging material off into space. If 3I/Atlas was exceptionally weak and fragile, it would explain everything. It wouldn't need a powerful gas engine to create a huge dust tail, it would just need to crumble. The dust we were seeing wasn't being blasted off, it was simply sloughing off, like stone from an ancient weathered ruin. The dust tail was not a sign of activity, it was a trail of debris from a slow-motion disintegration. This hypothesis changed the entire nature of the investigation. It meant our suspect was unstable, it was volatile, it meant there was a very real risk that as it reached its closest point to the Sun, the combined thermal, tidal, and rotational stresses would become too much. The suspect could break up entirely, dissolving into a cloud of dust and gas right before our eyes. The manhunt was no longer just about observation. It was now a race against time. The remote autopsy had revealed a fatal weakness. Now the global watch would begin, with every telescope trained on the visitor, waiting to see if it would survive its fiery passage, or if they would be the sole witnesses to the death of a traveler from another star. The investigation into the nature of 3I/Atlas was a forensic analysis of its past. The manhunt is a vigil for its future. With the suspect identified as fragile and potentially self-destructive, the timeline of its passage through our solar system became less of a simple calendar and more of a countdown to a critical event. Every astronomer, professional and amateur alike was now a witness, watching a cosmic drama unfold on a rigid and unforgiving schedule. The clock started ticking on May 7, 2025, the night the ATLS survey captured the first definitive images. At that point, the visitor was already deep within our territory, having crossed the orbit of Jupiter months earlier, an unseen ghost in the outer darkness. By the time it was officially announced, it was closing in on the orbit of Mars, traveling at a staggering speed of over 100,000 miles per hour relative to our Sun. The next critical date was August 29, 2025. On this day, the comet crossed the orbital path of Earth. It was still far from our planet in actual space, but this milestone marked its official entry into the inner solar system, the zone where the sun's heat and radiation intensified dramatically. This was the beginning of the true danger zone. The thermal stresses would now begin to climb exponentially, and the global watch for signs of fragmentation intensified. The most important date of the entire encounter is September 28, 2025. This is the date of perihelion. It is the moment the comet makes its tightest turn around the Sun, the point of its closest approach. It will pass just inside the orbit of the planet Mercury, subjecting it to the full, unmitigated fury of our star. The heat will be unimaginable. The gravitational tides will be at their most violent. If the suspect is going to break, if it is going to disintegrate under the strain, this is the moment it will happen. Perihelion is the climax of the story. After this point, assuming it survives, the comet begins its long journey back out into the void. But for us, the show is just getting started. Its outbound path brings it swinging up from below the plane of the solar system, setting the stage for the next key date, October 23, 2025. This is the day of its closest approach to Earth. The comet will pass our planet at a safe but cosmically intimate distance of just 18 million miles. This is our one and only window for the most detailed observations. It is the moment the world's most powerful telescopes will have their best possible view, and it is the moment that amateur skywatchers around the globe will have their chance to witness the traveler for themselves. From late October through November, it will be at its biggest and brightest in our skies, a fleeting guest on a journey that will last for eternity. The passage of an interstellar comet is not just a scientific event, it is a shared human experience. It is a chance for anyone, anywhere on Earth, to look up and connect with a visitor from another star system. But finding a faint fuzzy object in the infinite blackness of the night sky requires a plan. This is your guide to joining the global watch. First, we must manage expectations. This will not be a brilliant, dazzling object like Halley's Comet was for our ancestors. 3I/Atlas is not predicted to be bright enough to be seen with the naked eye, except perhaps from the most remote, darkest, and highest altitude locations on the planet, and even then only as an incredibly faint, barely there smudge. For the vast majority of us, optical aid is not just recommended, it is essential. The best tool for the average person will be a good pair of binoculars. Any standard bird-watching binoculars mounted on a simple tripod to keep them steady will be enough to reveal the comet. You are not looking for a sharp point of light like a star, you are looking for its opposite. Look for a star that seems fuzzy, out of focus. That hazy, ghostly glow is the comet's coma, the cloud of gas and dust surrounding its nucleus. In the weeks surrounding its closest approach in late October and early November, you may even be able to glimpse the faint streak of its dust tail, extending from one side. For those with an amateur telescope, the view will be even more rewarding. A small 4-inch telescope will transform the fuzzy smudge into a distinct object, showing a brighter core within the coma. Larger 8 or 10-inch telescopes may reveal the greenish tint of its diatomic carbon and provide a clear, detailed view of its dust tail. The where and when are crucial. During its peak visibility window, from late October to early December of 2025, the comet will be tracing a path through the prominent winter constellations of the Northern Hemisphere. It will rise in the east, late in the evening, and be best viewed in the hours after midnight, high in the southern sky. It is predicted to pass directly through the constellation of Taurus, gliding just below the iconic Pleiades star cluster before moving towards the feet of Gemini. Star charts and astronomy apps will be the essential maps for this manhunt, providing the exact coordinates for any given night. But the single most important factor is location. You must get away from the light pollution of cities. A trip to a rural park or a remote countryside spot will do more to improve your view than the most expensive telescope. There, under a truly dark sky, you can witness the ghost for yourself. While the public turns its binoculars to the sky, the professional astronomical community is engaged in the most intense and coordinated observational campaign in modern history. This is the Global Watch, a network of silent, powerful sentinels working in concert to squeeze every possible photon of information from 3I/Atlas before it vanishes forever. The effort is led by the titans of space-based astronomy. The James Webb Space Telescope is the undisputed star of the show. Its enormous mirror and unparalleled sensitivity in the infrared spectrum make it the perfect instrument for this investigation. The JWST is not just taking pictures, it is performing the deep forensic spectroscopy described earlier, but with a precision that ground-based telescopes can only dream of. It is analyzing the heat signature of the dust tail, searching for the chemical barcodes of complex organic molecules, and watching for the telltale signs of a breakup in real time. The Hubble Space Telescope, its older but still powerful sibling, is providing crucial observations in visible and ultraviolet light, tracking the behavior of specific gases like oxygen and hydrogen that the JWST cannot see. On the ground, a global network of observatories is providing 24-hour coverage. As the Earth turns, one telescope hands off the target to another. In Chile, the European Southern Observatory's Very Large Telescope is using its battery of spectrographs to monitor the comet's chemical output nightly. In Hawaii, the twin Keck telescopes are doing the same, providing a crucial cross-check on the data. The new Vera C. Rubin Observatory, in its first year of full operation, is using its gigantic camera to take wide-field images every few nights, precisely measuring the comet's trajectory and brightness, watching for any sudden outbursts or deviations from its predicted path. All of this data from every telescope flows into a central clearinghouse, the Minor Planet Center, operated under the auspices of the International Astronomical Union. They are the air traffic controllers for this event, collecting thousands of observations from professionals and amateurs alike, refining the comet's orbit with every new data point, and issuing updated alerts to the entire world. It is a massive, collaborative, and open effort. Every piece of evidence is being scrutinized by thousands of scientists. This is not just an observation, it is a stakeout. The world is watching, waiting for the verdict on the comet's fate and hoping to witness the secrets of another star system. The verdict on the comet's nature, a fragile but chemically familiar traveler, was in. But the final, most profound question remained unanswered. Where did it come from? To find out, astronomers had to perform one of the most astonishing feats of celestial forensics imaginable. They had to become time travelers. They had to trace the suspect's path backwards, not just out of our solar system, but across interstellar space, through the immense gulf of the void, for millions of years, to find its home. This is a task of staggering complexity. An object's path is not a straight line drawn across the galaxy. As 3I/Atlas moved through our solar system, its trajectory was bent and reshaped by the immense gravity of our Sun. The first step was to precisely calculate this gravitational influence and determine the exact vector, the combination of speed and direction, with which the comet entered our Sun's sphere of influence. This exit vector is the starting point for the interstellar journey. Once free of our Sun's grasp, the comet's path was then dictated by the subtle, collective gravity of the entire Milky Way galaxy. To rewind this journey, scientists rely on the single greatest map of our galactic neighborhood ever created: the data from the Gaia Space Observatory. Gaia has spent years charting the precise positions, motions, and velocities of over 1.5 billion stars. It is a celestial census of unprecedented detail. Using supercomputers, astronomers took the comet's interstellar trajectory and hit the cosmic rewind button. They calculated its path backwards in time, year by year, millennium by millennium. Simultaneously, they did the same for every star in the Gaia catalog, rewinding their orbits around the galactic center. The goal was to find a moment in the distant past, a single point in space and time, where the ghostly trail of the comet intersected with the path of a star. They were looking for a cosmic rendezvous, a moment when the comet was close enough to a star to have been thrown out of its home system. After weeks of computation, cross-referencing, and eliminating false positives, a candidate emerged from the data. The models showed that approximately 6 million years ago, 3I/Atlas was not a lonely traveler, but was part of the Oort cloud of a small, unremarkable star, a K2 dwarf, slightly smaller and cooler than our own Sun, located today in the direction of the constellation Aquila the Eagle. The analysis suggested that a close pass from another, wandering star disrupted that star's Oort cloud, dislodging the comet and sending it on its 6-million-year odyssey across the void. The verdict was in. The journey had a beginning. The traveler had a home. We had looked at a faint smudge in our sky and seen in it a story that began 6 million years ago, in the outer darkness of another solar system, light years from our own. The arrival of 3I/Atlas, following so closely on the heels of ʻOumuamua and Borisov, represents more than just another scientific curiosity. It represents a paradigm shift in our understanding of the galaxy. For all of human history until 2017, the number of confirmed interstellar objects was 0. Now, in less than a decade, we have 3. This is not a coincidence, it is a revelation. The truth is that these visitors have always been coming. Our solar system has been sailing through a constant, gentle rain of material from other stars for its entire 4.5 billion-year existence. We never saw them before for one simple reason. Our nets weren't fine enough. Our telescopes weren't powerful enough, our surveys weren't wide enough, and our computers weren't fast enough to sift through the data and find these faint, fast-moving needles in the cosmic haystack. With the advent of automated robotic sky surveys like ATLL, and the imminent arrival of next-generation observatories like the Vera C. Rubin Observatory, the floodgates are now open. We have finally built the tools to see what has always been there. Astronomers now predict that we will not be finding one interstellar object every few years, we will soon be finding several every single year. They are not rare miracles, said the lawyer, closing. This realization has profound, almost philosophical implications. It means the solar systems of the galaxy are not isolated islands. They are connected. They are constantly exchanging material. The building blocks of our solar system, the water, the carbon, the cyanide found in Borisov and Atlas, are not unique to us. They are the standard galactic recipe. Each new visitor is a free sample, a piece of another world delivered to our doorstep, allowing us to do comparative planetology not just for the 8 planets in our family, but for the countless planets across the galaxy. And this leads to the most tantalizing implication of all, panspermia, the theory that life itself can be transported between star systems. For centuries it was pure speculation, but now we have the evidence. We see the vehicles. We have confirmed that comets, which are rich in water and the organic molecules necessary for life, are durable enough to survive the journey between stars. If life can begin on one world, and if that world's comets are regularly ejected into the galaxy, then the arrival of each interstellar visitor is a reminder that the seeds of life may not be confined to their home planet. The galaxy may not just be exchanging rock and ice, but biology itself. The floodgates have opened, and with them, a whole new realm of possibility. The investigations of the first 3 interstellar visitors have been masterpieces of remote forensics. We have studied them from afar, decoding their light, tracing their paths, and deducing their nature. But this is only the beginning. The next step in this journey is not to wait for the evidence to come to us, but to go out and meet it. This is the goal of one of the most innovative and exciting space missions ever conceived, the European Space Agency's Comet Interceptor. Comet Interceptor is a new class of mission, designed specifically for our new reality. It is a rapid responsive probe, a sentinel designed to perform the ultimate manhunt. Scheduled for launch before the end of this decade, the spacecraft will not be aimed at any known target. Instead, it will travel to a gravitationally stable point in space, about 1 million miles from Earth, and it will wait. It will park itself in the darkness, dormant and patient, like a predator waiting for its prey. Its target does not yet exist in our catalogs. The mission will wait for our powerful sky surveys to discover the next suitable visitor. The ideal target would be a pristine comet from our own Oort cloud, making its very first journey towards the Sun. But the ultimate prize, the mission's dream target, would be the 4th interstellar object. When that target is identified and its trajectory is confirmed, Comet Interceptor will fire its engines and begin a high-speed chase, a journey of months or even years to make a rendezvous with the visitor deep in space. As it approaches the comet, the spacecraft will deploy 2 smaller subprobes, The 3 spacecraft will then fly through the comet's coma in formation, creating a 3-dimensional profile of the object. One probe will study the nucleus itself, another will sample the gas, a third will analyze the dust. This is the future. We will no longer be limited to analyzing the faint filtered light that reaches Earth. We will see a nucleus with our own robotic eyes. We will fly through its tail. We will taste its chemical makeup directly. The remote autopsy will be replaced by a direct physical examination. The story that began with a silent alarm from ʻOumuamua, that was clarified by the familiar passage of Borisov, and that was brought into sharp focus by the fragile beauty of Atlas, is now driving us out into the solar system. We are no longer just passive witnesses. We are becoming active explorers. The next time a stranger from another star system enters our territory, we will be ready. We will be waiting, and we will go to meet it.